Kitchen Table Astronomy at the Amherst Kitchen Table of Hampshire College astronomer Dr. Salman Hameed, our very own Mr. Universe. We live in an era where A, people doubt that science is real, despite lots of evidence, and B, where people don't like to admit that they're wrong. Science can be real and also admit that it's wrong when new science happens, and that's what the topic of our conversation is today.
Yeah, I mean, I thought sometimes you have to just take a deep breath. I mean, I create videos on YouTube as well for audience for South Asia, but also this also goes on YouTube too. And you get comments, something like blanket statements. Oh, for example, Big Bang. Oh, this is all wrong, or so and so forth. Like completely dismissive to science, and oftentimes people go like, "Oh, you can't trust science. It says one thing one day, another thing in the other." So basically, everything is relative. And sometimes that is true that things change, and in fact, for scientists, in an ideal way, and scientists are humans too, contrary to sometimes what people believe, but no, we are humans. There is a big thing. The way to do that is you can love your theory, you can love your idea, but if the evidence goes the other way, and you go like, yeah, I was wrong. And that is also part of history of science. Sometimes people do it more graciously, easily, and sometimes not. But what is out there is what is out there. And I think that's a good story. But what I wanted to point out today was prompted by some of our recent conversations, and we often talk about, for example, galaxies or supermassive black holes. We've been talking about that are at the center of galaxies. And we know both of those things exist. But galaxies, this is something that we know. Our Milky Way is a galaxy. People talk about, hey, Andromeda galaxy, that is sort of like, right now in the nighttime, you can also see it, that it's a galaxy like ours, about a few million light years away. And that is the nearest spiral galaxy. And our universe is full of galaxies. You have more than 100 billion galaxies. And people go, wow, by looking at Hubble Space Telescope images or James Webb images of Hubble Deep Field or James Webb Deep Field, so on and so forth. But 100 years ago, in 1924, in fact, if we were having this conversation, and we'd be like, are those galaxies like the Milky Way? That was a big debate. And some people argued, including a famous astronomer, Harlow Shapley, he argued that actually those are spiral nebulae. You could see the shape as spirals from the telescopes at the time, but we didn't know how far they were. And so Shapley, who was an astronomer, argued that they are actually not very far away. They are part of the Milky Way, and he thought the Milky Way itself is much bigger, not like millions of light years across, but a few 100,000. And these Andromeda nebula, for example, is part of the Milky Way. Then there were others, like, for example, Edwin Hubble himself. He thought these spiral nebulae, like Andromeda, actually they look very small, but they look small because they are very, very far away.
How did Hubble figure out that they were very, very far away? And this ties into an overshadowed person in the history of astronomy.
And so again, we are talking about 100 years ago, right? So this is not like, 500 years. 100 years ago, the question was, well, what is the nature of these spiral nebulae? And the biggest problem in astronomy is that of distance. I mean, if you look up, you are seeing basically like a planetarium. You are seeing a two-dimensional sphere, or sort of like, around us, a dome, but you don't know how far away things are. And so for astronomers, that is a key thing to determine, because if something is faint or small, is it because it is far away, or it is because it is intrinsically faint or small? And so this is a perfect example to that. So you have to figure out, you have to find a way to find distances to objects. Now, for a few 100 light years away and relatively nearby stars, we can use something called parallax. And parallax is something that basically your eyes do in terms of measuring distances. You can actually put a finger in extend your finger in front of your eyes, and you can close one eye and the other, and you will see your finger basically appear to move with respect to the background object. And if the finger is close by, the movement is going to be far more.
Oh yeah, I just did it.
If it's farther away, the movement is going to be less.
Everybody should try this, unless you're driving.
And so you can basically, by the movement of it, the finger is not moving. It's your eyes that you are shutting off left or right. The finger appears to move with respect to the background. If it moves more, it's closer. Less, it's farther away.
That's so cool.
That's how a brain interprets, because of the two eyes. It interprets in terms of distances to things. And so that's a very powerful technique. It's very good technique. You can easily figure out from trigonometry how far away something is based upon the movement. And we can use that movement because of the Earth going around the sun. And so in 6 months' time, so you are at one side of the orbit, and then 6 months later, you can actually look at the same star, for example, from the opposite side, and you can see if how much the star has moved with respect to the background faraway star.
So that's like 6 months from now, it's like your left eye, and right now is your right eye. Camera 1, camera 2, with your eyes, with the planet in its rotation. That's how some stars and galaxies are figured out.
Well, not galaxies, just stars.
Okay.
Because this would only work in the same way if your finger, the example, if we go back to it, if you can extend it to about a mile, you can switch your left eye or right eye as much as you want. You will not see anything move in the background because it's too far away.
Okay.
And so this particular technique of parallax works for stars that are nearby. And for telescopes, we've used sort of like, to about 1,000 light years or so. And after that, it becomes too hard to measure any variation, any movement of that star with respect to the background within that Earth-Sun distance. But now, with other satellites, with other telescopes, you can extend it to a few 10,000 or so light years or so. But this is a very good technique, but still relatively close by. So you need to find something else, and that one of the most important things that allowed us to find distances is a star. It's a particular type of star. It's called a Cepheid variable. And it basically, what we know about that is it's a stage of a star that is bigger than our sun, and it varies in brightness. So these big stars go through a stage of about a few tens of thousands of years. So again, not very long, but few tens of thousands of years, where these type of stars vary in brightness. They become big and small for very specific physics purposes, which we understand very well. Their atmospheres basically become smaller, and as they become smaller, they got hotter, and then the sort of like, it expands back up, and then they get a little bit cooler, and it varies systematically. So, for example, some Cepheid variables would have this period of brightness and dimming and brightening for about 5 days. Some would have 10 days, some would have 15 days. And so you can actually find these variable stars with very specific brightness pattern. Okay, so that's well and good. But here is the thing. There was an astronomer, Henrietta Leavitt. She lived in the early 1900s, and she discovered that there is a relationship between this period of their variation and how bright they actually are. And this is called period luminosity relation, or the Leavitt law. And this was crucial because in some ways this tells you that if you can figure out what their brightness level, how many days it is changing, it's taking to change its brightness, it will tell you how bright it actually is. Now, if you see it, if it's faint, that means it's far away. If it's bright, it means it's close by. It's like if you have a flashlight and you know it is 50 watts bulb in it, and if you are close by, you would see that same flashlight much brighter. If you see it as faint, and it's a same 50-watt bulb, you know that it's far away.
So because Henrietta Leavitt could figure out by this fluctuation in brightness how bright a star actually was, she could then tell that star must be far away because it's faint, as opposed to closer because it's brighter.
Well, so she used, so this was in the early 1900s. She was working at Harvard, and she was given these photographic plates. And she was looking at a lot of these stars in the small and large Magellanic Clouds, which are in the southern hemisphere. And there was a Harvard Observatory in Peru. And she was asked to look for these variable stars, Cepheids. And she found, I think, around 17, if I remember the number, actually, number sticks in my mind because it's like 1,777 Cepheid variable stars that she identified in these Magellanic Clouds. At that time, they just looked like people thought they were part of our own galaxy. Now we know those are our satellite galaxies. Out of those, 25 she identified as Cepheid variables, and they were all part of small Magellanic Cloud. So she knew they are all part of the same cloud. They are all at the same distance. Now you can just measure their variation, their period, and you can figure out whether they are bright or dim, but you know it's the same distance. So you can actually figure out what period leads to what kind of brightness. So this was amazing. She actually published that paper, I think, in 1912 or 1913. That was extremely important because if you can identify a Cepheid variable somewhere, you can figure out, you can measure its period. How long is it taking for it to dim and bright? And you can tell what its actual brightness is. And then all you have to do is how bright it appears. And it can tell you the distance. So this was so to me, first of all, I mean, even if you don't get into the details, this is incredible that we figured out that here is a star. We understand its physics, what's going on. It is getting brighter and dimmer. And they go, you know what? We can actually use that to figure out a distance. And this is precisely what Edwin Hubble did. Because Hubble was he thought Andromeda Nebula was actually quite far. There were others who thought, no, actually this is part of our own galaxy. And so he explicitly was looking for Cepheid variables in Andromeda galaxy. And he found one in 1923. So almost 100 years ago. It was in October of 1923 when he first made an observation of the Cepheid variable. There is a photographic plate. And same thing with Henrietta Leavitt also, by the way. I just find it amazing, like, that they were using these plates, and identifying how things over a period of time, are they changing or not. So Hubble looked at this star that had varied over a period of time, and he identified it. That particular plate, I think it's now saved in sort of one of the museums for that, and he identified Andromeda Nebula. It's there, and he wrote VAR, a variable, and that was a Cepheid variable, and that clinched the fact that Andromeda is actually quite far. And today we know that it's over 2 million light years away, and it's a galaxy like ours. And Monte, you had mentioned about admitting that you are wrong. So this other astronomer, Harlow Shapley, who actually thought that that is not the case, that Milky Way is really big and these spiral nebulae are part of the Milky Way. Hubble wrote him a letter and sending him his results, and he seemed to have said that this letter destroyed my universe. And then he went on to actually use Cepheid variables to actually determine where the sun is located with respect to the Milky Way. And now we also know that actually, sorry to disappoint, but we are not at the center even of our own Milky Way. We are located about 30,000 light years from the center. So that particular aspect is also tied to figuring it out, distances to different objects, to map out our own location. And that is also, a lot of that stuff centers around using Cepheid variables that came from Henrietta Leavitt and Leavitt's law. And in fact, Edwin Hubble actually nominated her for a Nobel Prize when he discovered the Cepheid variable in Andromeda. So he nominated her for a Nobel Prize, and if I remember correctly, the Nobel Committee also wanted to approach her for the 1925 Nobel Prize. Unfortunately, she had already died in 1921, and Nobel Prizes are not given posthumously, so she never got that.
But if it weren't for Henrietta Leavitt's math, we wouldn't know how far away things are. If it weren't for Hubble trusting that math, we would think perhaps that the Milky Way was the only galaxy, or at least these other galaxies that we know about were part of the Milky Way. Hubble's telescope then goes on up in the sky to take a deep field image, to just open its lens for a long period of time in a patch of sky that we thought was dark. And what happened?
Well, and so it found out sort of like all these galaxies. It was supposed to be an empty patch, but it turns out to be full of galaxies. And I should actually close the loop regarding that. One of the key projects of Hubble Space Telescope was actually to look for Cepheid variables in other galaxies, because then we can find out more about other galaxies, and that actually leads to sort of like, the expansion, because then you can measure the expansion of the universe and so on and so forth. But ultimately, if we can come back to where we started, this is one of those cases that this is not changing. We actually do know this is like Earth goes around the sun. If you think, well, science says one thing one day, one thing another, that is not the case. We actually do know, the Earth is going around the sun relatively. And the same way we do know that the Milky Way is just one of the galaxies, and Andromeda is another galaxy a few million light years away, and that the universe is full of galaxies as seen by, apart from other things, but including Hubble Deep Field as well, and that we are not at the center. Our solar system, our sun, our Earth, we are not at the center even of our Milky Way galaxy. And we just happen to be 30,000 light years from the center. So when we think about our own perspective, we have to take that into account. We cannot just make stuff up that, hey, we are really important. We ought to be at the center. Well, but we are not. And so then people have to figure out how to think about importance in a different way. And if I can add that, I think the sense of importance, maybe one way to think about that is that even though we live in this sort of like completely ordinary neighborhood, 30,000 light years from the center of the galaxy, nothing is happening here, all the action is downtown of the galaxy. But we can figure these things out, that Henrietta Leavitt used these star brightness to figure out, hey, we can use those for distances, and then from there we can figure out how unimportant we are. I think that is really cool, and I think that's what makes us important.